Look at the headlines today, and you will see a recurring prediction. Artificial intelligence software is advancing so rapidly that total replacement of the human workforce is an absolute certainty. This anxiety relies on a specific assumption. It assumes that exponential software scaling can continue indefinitely, operating as pure mathematics floating in the cloud, completely detached from the physical world. But the people selling this inevitability are ignoring a hard physical limit. Generating artificial intelligence requires concrete infrastructure, and our global power grids are already straining to provide the necessary electricity. We have to look at the unit economics of computation. Every time an AI model generates a response, it produces silicon thought, and that thought carries an unavoidable, heavy physical cost in joules and watts. Compare those massive industrial-scale data centers with the human brain. The biological mind operates on a strict budget of about 20 watts, roughly the power of a dim light bulb. It is an impossibly efficient edge device. By auditing the global power grid and semiconductor physics, we can see exactly why biological intelligence remains the most economically viable processor on Earth. Total workforce replacement is a physical impossibility. The root of AI's massive energy consumption dates back to 1945 with the creation of the von Neumann architecture. This is the foundational hardware design blueprint that almost all modern computers still use today. For AI, this blueprint has a critical flaw. It separates the CPUs from memory. To generate text, models shuttle billions of neural weights across this narrow channel. Math uses only 10% of energy. 90% is wasted moving data, the von Neumann tax. It is the hardware equivalent of executing a full table scan across a massive columnar database just to answer a basic single-line query. The effort required is entirely disproportionate to the actual work being done. Scaling up AI models only makes this worse. As models grow, they exceed the local memory capacity of a single graphics processing unit, or GPU. The data is forced to travel even further across interconnects between multiple chips, compounding the energy waste at every level. The AI energy crisis is not a software bug that can be patched. It is a hardware failure baked into the silicon itself, making pure algorithmic scaling a thermodynamic dead end. Now, contrast this with the biological alternative. The human brain operates on a strict 20-watt power budget, completely sidestepping this data movement penalty. In biological systems, there is no separation between components. The synapse acts as both the processor and the memory simultaneously. Biology also utilizes sparsity. Neurons do not fire continuously. They only consume energy to transmit electrical spikes when specific thresholds are met, keeping metabolic waste near zero. Compare this elegant biological efficiency with the sheer brute force required by a modern exascale supercomputer to achieve a similar computational throughput. An exaflop is a measure of computing performance equal to 1 quintillion calculations per second. To achieve that rate on silicon architecture requires 20 megawatts of power, 1 million times more energy than the brain uses. Look at this scale comparison. If we attempted to run a real-time digital twin of the entire human brain on current hardware, it would require 2.7 gigawatts of power. Attempting to match complex human logic on von Neumann hardware is so inherently inefficient that it constitutes an unsustainable tax on our global infrastructure. For years, AI capability grew by simply adding more graphics processing units into standard server rooms. But those easy, early gains have been exhausted. We have reached a thermal crisis. Data center rack densities are now pushing past 100 kilowatts, causing traditional fan-based air cooling to completely fail under the intense heat load. The industry is undergoing a mandatory shift to liquid cooling systems. Without them, the newest 1200-watt AI chips would literally melt themselves. This chart shows the trajectory of AI progress over time. The blue line represents linear gains in software benchmarks, but the red line tracks the required gigawatts and cooling infrastructure. It diverges into an exponential parabolic curve. The conventional electrical grid cannot sustain this parabolic energy demand, forcing major tech companies into a drastic pivot. Cloud providers are now building atomic moats. They are securing proprietary agreements with nuclear power plants simply to guarantee the baseload electricity required to run future models. A person requires 0 megawatts of cloud infrastructure and absolutely no liquid cooling to operate effectively every single day. To fully replace human labor through silicon brute force, we don't just need better code. We need atomic-backed grids, making widespread workforce replacement physically impossible. Ultimately, workforce viability comes down to the unit economics of thought, the financial cost required to produce a single unit of cognitive output. For a single-step task, AI is incredibly cheap, costing just 10 cents. Contrast that with human labor. Paying a professional for that exact same isolated task could cost $400. For simple, high-volume output, human time is significantly more expensive. But the equation flips when we look at long-horizon tasks, complex workflows that require thousands of connected steps, active tool use, and continuous adaptability over months. For humans, labor costs scale linearly. A worker's salary remains constant regardless of the day-to-day cognitive complexity or how many steps a project requires. For an AI, the cost of long-horizon tasks scales quadratically. To overcome compounding error rates and software hallucinations over thousands of steps, the required compute multiplies exponentially, destroying any cost advantage. Silicon thought is economically viable for high-volume, low-complexity tasks, but for complex project management, human thought retains a massive, unbeatable economic advantage. The human worker is not a biological relic destined for obsolescence. You are a highly optimized, self-contained edge device. Operating on just 20 watts, you process multimodal inputs, manage long-term memory, and execute complex logic locally without ever needing to ping a 20-megawatt cloud cluster. Artificial intelligence is an incredibly powerful specialized tool, but its potential is physically trapped by a hardware paradigm designed in the middle of the 20th century. Until the semiconductor industry structurally reinvents computing hardware to mimic the integrated synapses of the brain, embodied human intelligence remains the ultimate, unbreakable economic moat.